So we're going to talk this morning about open channel flow. So this is our reach routing methods. So yesterday we talked about transform, which is kind of how we define the hydrograph in the subbasin. And so now we're going to talk about the hydrograph as it transforms through the routing reach, right, through our river channels. All right, so the goal of this presentation is to talk about open channel flow processes and the different options in HMS. So we'll talk about like rules of thumb, how you can pick a method, how you can parameterize the method, and which ones are appropriate for different conditions, right? Because there's a lot of different types of rivers and not every method applies to every river. So yesterday, we talked a lot about the transform. And so this was covering this portion, which is overland flow, right? So we have water. Once our precipitation exceeds our loss, our infiltration rate, then it becomes surface runoff. And it starts to collect along the surface into these little rills and channels, and eventually making its way downstream into larger rivers and channels. And so that transitions from overland flow into channel flow, open channel flow. And so once it's in the channel, it's defined by attenuation and translation effects, which we're going to talk about. But the processes are a little bit different between overland and once we get into open channel flow. Right, every river is different. You might select different methods for different types of conditions. Does anyone know any of these? Can I get some guesses? Yeah, so this is Great Falls. It's actually a national park near DC. So that's on the Potomac River. Really cool if you haven't been there before. You can even just guess states. I know some of these are like not going to be well known. Which one? This one's Colorado. This is also Colorado. This is also Colorado. I'm from there. I have a lot of pictures of Colorado. Any guesses on this one? No, but it looks similar. It is sort of in the east. No, a little farther south. This is Arkansas. This is the Ouachita River downstream of Blakely Mountain Dam. Anyone work on that dam at all? No? All right. Believe it or not, this is actually a river, not a lake. This is the Sacramento River, right by Sacramento, which is notoriously flat, which is why it floods, because the elevation of this is like 25 feet above sea level. And like remember how far it has to travel before it gets to the ocean. So it's very, very flat, very prone to flooding. This is just a little tiny creek in Virginia. This one's cool. This was after a lot of snowmelt in Colorado. So I think this is a really good example of like what bankful means when we say bankful. This is a good picture of that because it's right up to the edges, if not a little bit above the bankful stage for this particular conveyance channel. Anyway, a lot of different rivers, right? The conditions between this one and this one are going to be extremely different when we model them in HMS. Some of the HMS methods might not be appropriate at all. I'd say for this little Virginia Creek and the Sacramento River, HMS probably can't handle that because the slopes are really, really low. And so you have to use more hydraulic type analyses. And so we'll talk about different conditions that different methods apply. All right, so reach routing, right, we're trying to represent the hydrograph and how it changes as it travels downstream. And so we start with this blue hydrograph at the beginning of the reach, and then by the time we get to the end, we have our pink. And so the changes of the hydrograph over time are due to translation, right? It takes time for it to travel. And so that's this travel time component where the peak is delayed in time. And then we also have this attenuation effect, which is kind of the flattening of the hydrograph. And so you can see the reduction in the peak. That's caused by diffusion, which is like a reduction in energy. And so that causes everything to flatten out. And so the goal of hydrologic routing is to model and estimate how the shape of the hydrograph changes. So this is an example basin. You guys have seen this before. you're going to see it again. And so we have a couple subbasins upstream. In each of those, right, we use our transform to determine the shape of this hydrograph. And those will get routed to this point here. So now we have to get those hydrographs from this point to this point. And what we do is we combine them together and we put it through a reach element. And so then we can see the translation and the attenuation effects as those hydrographs are combined and then routed downstream. And so just keep in mind, so anytime you have subbasins above an outlet, you're going to have a reach in between to be able to get those hydrographs down. This subbasin here is just going to meet you at the outlet, right? So we're not like combining flow in between. So right, that's a simplification that we're making in HMS. So just keep that in mind. Reach routing applies to a lot of different scenarios. Most studies are going to have to use reach routing, but the methods you pick will depend on the goals of the project and the type of the channels that you have. And so, like, depending on which study you have and what the needs are, what the output needs to be, can help decide like which method to use. But almost all HMS projects are going to have reach routing. So there's a slight difference between hydrologic and hydraulic reach routing. So hydraulic routing, this is mainly what drives RAS, if anyone's familiar. It's based on solutions of partial differential equations, which hopefully at least somewhat remember from fluid mechanics. We call it the St. Venant equations, also called the dynamic wave equations. And that consists of the continuity and the momentum equation. So those combined make up the dynamic wave equations. For hydrologic routing, we make some simplifications. So we still use continuity and momentum, but we use a simplified version of them. And then sometimes we just replace the momentum equation with a storage discharge function. So I'll show what the different simplifications are, but we're using the same concepts, right? But we're making it a little bit more simple than full-on hydraulic routing. So this is the two equations. Sorry that we're going to be talking about a little bit of math this morning. I know it's kind of early. The St. Venant equations are these two combined, continuity and momentum. And these are for one-dimensional unsteady flow. And the continuity equation is essentially conservation of mass, right? So we care about the volume and how the volume changes in the channel. So we have flow coming in, we have some storage within the channel, and then we have flow coming out. So that's essentially what the continuity equation is. The momentum equation, which I also wrote over there, is essentially the changes in forces on the body of water as it moves through the channel. So we have gravitational forces, friction forces, and pressure forces. And so those combined, we call a friction slope. That's how we define kind of how those forces are. So that's this SF term. And this is St. Venant himself. All right, so as I mentioned, in hydrologic routing, we make simplifications, right? We're not going to model every aspect of the momentum equation. And so depending on which terms you use, we call that an approximation. So if you only use this first term, which is the bottom slope I have written over there, if we only use this first term, that's called the kinematic wave approximation. So that represents steady, uniform flow. And I'll show a couple methods in HMS that use this approximation. If we use the first two terms, that becomes the diffusive wave approximation, right? So that represents steady, non-uniform flow. And we have a couple methods in HMS that use that approximation, right? They'll use a couple more parameters. If you use the first three terms, that's called quasi-steady state dynamic wave approximation. Now we're getting into RAS land. HMS doesn't handle this approximation anymore. And that represents steady, non-uniform flow. And then the last is if you're just doing all of the terms, if you represent the entire equation, that's full dynamic wave. So we don't have to worry about these. This is RAS land. So just kind of keep in mind the first two. We're either going to use the first term or the first two terms, and that's the simplifications we make in HMS. So that's really the takeaway from this. All right, the reason we can make these simplifications is that the first term is typically the most impactful. And so there was this study by Henderson in 1966 that looked at essentially what is the magnitude of values in a steep alluvial stream. And so for each term, these were the values that were estimated. So we can see this first term has the biggest impact, and that's why we can make these approximations, especially for the steeper the channel, the more that these approximations apply. As the channel gets more and more flat, these terms on the end become more and more important. And so that's why a flatter reach typically needs to include more of these terms. And so it gets harder for us to estimate in HMS. For one-dimensional routing, we have to make a couple assumptions. We assume that velocity is constant and that the water surface is horizontal, which isn't true in a lot of real channels. We assume that the flows are gradually varied, right? So we're not going to have sudden changes in flow like a hydraulic jump. We assume there's no lateral or secondary circulation. It's kind of a fixed channel so that we can estimate fixed volumes as it moves through the channel. There's no erosion or deposition, right? So we're assuming that the channel dimensions stay the same throughout the course of the simulation. And we assume uniform density of our water. So these are all of the assumptions that we're making when we perform this routing. So keep that in mind that we do have to make simplifications. All right, these are the methods that we have in HMS. As I mentioned before, they're either going to be using the first term or the first two terms of the momentum equation. The first set of these are the hydrologic routing. Straddle stagger we're probably going to get rid of soon. So typically these top 5 are used the most. And then we also have a couple of hydraulic routing methods, which Greg talked about yesterday. It's actually part of the transform, so it'll be part of the subbasin. But if you remember, like 2D diffusion wave, that uses 2D mesh from RAS, right? So it can do a little bit more of the hydraulic routing as opposed to hydrologic routing. And so if you end up needing more detail in your routing, or if you need to model like a really flat area, this would be a better method to choose. These hydrologic routing methods are going to typically be a little simpler, so they're pretty common. So we're going to talk about a couple of these specifically, and then in the workshop, you're going to apply them and practice using them. For estimating the parameters for the different methods, again, we have GIS at our disposal. And a lot of these methods are very physically based, and so it's really easy to just directly use the values that we get from GIS. So the National Hydrography Dataset, that's our stream channel shapefiles. So that can help get stream length, especially if you don't have, if you haven't done that yourself in HMS. The National Elevation Dataset, NED, so that gets us the topography, so that can get you slopes and changes in elevation. And the Land Cover Database can help with impervious area. And I think on Tuesday, Lauren gave a presentation about GIS parameter estimation, right? So you can calculate these directly in HMS if you have the GIS files loaded in. So if you open the reach characteristics, this is what it looks like on the right. This is a lot of the terms that you'll be using when you parameterize these methods. And so a lot of times you'll be using the length or the slope for the reach. So just a quick way to grab some of these values. But yeah, for these reach methods, it's pretty easy to get the data that you need compared to other loss methods. All right. So the lag method is the first method we're going to talk about. I'm going to start out with a caveat please don't use this method. It's very simple, and in most cases it's too simple. We still talk about it just because it helps represent the concepts, but there are pretty few instances where this will apply. So it only represents translation, right? That's the change in the hydrograph over time. So there's no attenuation, right? So there's no reduction in the peak due to that diffusion effect. It's only going to translate exactly this hydrograph, copy and paste hydrograph. So that's the biggest limitation. If we go back to our St. Venant equations, continuity and momentum, like I said, most of the HMS methods are going to be making simplifications of these equations. So the first simplification is we just don't use continuity at all. So we replace that with inflow equals outflow. And then momentum, we just completely don't use it at all, right? So it's a very simple method. It essentially isn't using our continuity and momentum equations, and it's just only accounting for direct translation. So this is what it looks like in HMS. There's one parameter, which is this lag, which will be in minutes. And it just defines what is the travel time at the start of the reach to the bottom of the reach. So this is what that looks like. You can see the hydrograph shape looks exactly the same, and it's just been translated in time. Same with this table. At the beginning and the end of the reach, the peak is the same, and the time of peak has changed by 6 hours, which is equal to our lag time, 360 minutes. So estimating lag time, again, it's equivalent to travel time in the reach. And there's 3 ways to estimate it. So if you have observed hydrographs at the start and the end of the reach, it's pretty easy to estimate. You can do it based on the centroid, based on the peak, or based on the middle of the rising limb. Those are typical ways to estimate. But a lot of times you're not going to have observed hydrograph at the start and the end of the reach, and so we typically use these other 2 methods. So the second one is to compare the length of the channel to the velocity of the wave, and that gives this parameter k. So we'll talk a little bit more about how to get that in a future method. And then the last way is to use regression equations. So sometimes regionally, they've taken empirical data and come up with an equation that relates like either subbasin size or elevation to lag time. And so if that's available to you, it's going to be like on a regional basis. So, right, some of our tutorials like have been developed mostly for Pennsylvania. So don't use those exactly if you're doing a study in like California or Nebraska, like it might not apply. So just keep that in mind that these are regionally developed. So I'd say more common to use this second method to estimate the lag time. Yeah?
Really basic question, just on routing in general. Is it basically just describing like what happens on a reach from like the upstream end to the downstream end? So it's taking those inputs and then inputting output.
Yeah, exactly. So the question is just re-summarizing what the reach routing is. And so we essentially have a hydrograph at the beginning of the reach, which will be this hydrograph in blue. And we want to predict what the hydrograph will look like when it gets to the end of the reach. And so that's what this black dashed line is. So we're just trying to figure out what happens in between when it travels from point A to point B. So now that it's at point B, what does the hydrograph look like? Alrighty. I'm going to skip calibration techniques because you can't really calibrate much on the lag method. Essentially, you can match the timing, and that's all that you have, right? If you're not matching the peak, you can't really do anything about that. That's a big limitation of the lag method. And so we'll talk more about calibration techniques in the future methods, but for this one, all you can do is shift the hydrograph back and forth if you have observed data. So advantages, it's very simple. There's one parameter. Disadvantages, it's too simple in a lot of cases. It doesn't account for attenuation. It's not really tied to measurable characteristics, right? The lag time does have some physical meaning, but you still typically need observed data to calibrate that parameter. And it's only appropriate for streams that don't experience attenuation. So that's going to be typically like really short stream channels. Like that's most of the time when this would be applied. And so keep in mind, in your HMS basin model, you don't have to use the same method for every single reach, right? So I've seen a lot of times if there's like a really shallow portion while the rest of the watershed is very steep, you might use one method for all the steep areas and a different method for the shallow area. So that's a good way to limit how many parameters you have to do if you can do simplifications in parts of the watershed and then do more detailed somewhere else. So don't be afraid to mix and match. I've seen as many as 4 different reach methods in one model. So that's okay. All right, the next method we're going to talk about is the Muskingum method. This was developed for the Muskingum River in Ohio. That's where it got its namesake. And it essentially is meant to accommodate this like looped relationship between storage and the channel. And so the idea is that in the rising wave of the hydrograph, it stores more water than in the falling wave. And so that's what this kind of looping effect is. And so in the parameters, it's going to account for that looping effect, mostly in the continuity equation, right? That's the one that counts for storage in the channel. So a good way to visualize this, it's typically defined as like a prism and wedge type storage. So this prism storage, this is kind of our like steady flow portion, and then the wedge is our unsteady flow portion. And so there's our prism, there's the wedge. So it's split up into 2 parts. And that's kind of how the method is going to be calculated behind the scenes. So I mentioned that like looping effect. So on the rising limb, we have positive wedge storage, right? We have more storage on the rising limb. And then on the falling limb, we have negative wedge storage, right? So we're storing less water on the falling limb of the hydrograph. So there's our steady flow portion, unsteady flow portion, steady flow portion, and our negative wedge storage. If we go back to our 2 equations, right, we're going to make some simplifications. So for this method, we replace continuity with inflow minus outflow is equal to our change in storage over time. So kind of what that looks like. So it's essentially representing a chunk of storage, right? That's inside our channel. We have flow coming in and flow coming out. So that's how we simplify the continuity equation for this method. And then for the momentum equation, we are doing just the relationship between storage in the reach and discharge at the outlet. So this is a storage discharge curve, if you've seen those before. And so those can be developed empirically, and they can also be developed using like a RAS model. And so we just use that storage discharge parameter table. This is what it looks like in HMS. There's a couple parameters, the Muskingum K, the X, and the number of subreaches, right? So these are the 3 parameters that we use in HMS. The K is our translation parameter, and the X and the subreaches define the attenuation, right? So the reduction in the peak. And so you see this, the peak is reduced a little bit, and the time of peak, 7.5 hours, equals our Muskingum K, right? So we can see that over here with a 7-hour delay between the peaks and then a slight reduction in the magnitude of the peak. So we'll talk about these 3 parameters and how you estimate them and kind of what they mean. So the first one, K, this is going to be pretty much the same as your lag that we just saw. And so it represents the travel time through the reach. And you can estimate if you have flow data at the start and end, which you typically don't, but if you do, it's very easy to estimate. You can compare the length to velocity. We talked about that with the lag method, or you can use regional regression equations, right? So we've seen this before. For actually calculating this length over velocity, talk a little bit about how you can do that. So you could use the Manning's equation to do that, and we can also use this Kleitz-Seddon law. And so what that says is that we can approximate the flood wave velocity. That's that, this bottom term right here. We can estimate that using the rating curve for the channel. So that's a little bit easier to get. USGS, most of their gauging stations publish this, like in the metadata. It's kind of tricky to find, but it's out there. Or it can be developed, maybe your district develops it, or any regional studies. And so we can estimate the velocity of the flood wave as the slope of the rating curve divided by the topped width of the channel. And so if we were to, for a given flow rate, we can estimate the slope of that and then divide that by the top width, and that gives us the flood wave. All right, so this X term, remember this is one that helps define attenuation. It doesn't have a lot of physical meaning, so there isn't really a definition for it. It's a dimensionless coefficient, and it's essentially like a weighting for how important the wedge is compared to the prism. When we look at the, if you remember the wedge and prism plots. So it affects the attenuation rate, so that's the reduction in peak, the spreading out of the hydrograph. And it's only between 0 and 0.5. Those are the limiting bounds. If you were to put something else in HMS, it'll give you an error. So when x is equal to 0, then we're assuming maximum attenuation. And when x is 0.5, we're saying no attenuation, it's only translation, and you're essentially going back to the lag method. Right, so typically it's recommended to just start in the middle, 0.25, and calibrate from there, depending on how much attenuation that you want. But this really just controls the amount of attenuation, so it's going to cause the peak to go up and down. So you can see that over here. 0.4, that's going to be close to no attenuation, so the peak is higher. And then we have a lower x of 0.1, and that reduces the peak closer to maximum attenuation. All right, the number of subreaches, this also affects the attenuation, but it essentially is like breaking the reach up into smaller components. And this just helps like numerically cause stability. Otherwise, the calculations can go unstable if the reach length is too long. And so it's related to our K, our lag parameter, and the computation time, right? The time step of our simulation. So keep that in mind. If you use this method, the Muskingum method, and you change your simulation time interval, you have to go and change your parameters in this method. So that one's kind of tricky because if you're running like an hourly time step and you say I want to switch to 15 minutes, you have to go in and change the number of subreaches because it is tied to that time step. So ideally, your time step is equal to K. And so since we typically have a much larger K value than the time step of our simulation, we split it up into smaller subreaches. So that's what this number of subreaches parameter means. And so that's typically estimated as an initial estimate, K divided by delta T. So that gives you basically how many subreaches you need for K to equal T. But then there's in a lower limit, 2 times K times X. You should not have a simulation time step that's less than that. So just keep that in mind. You're not going to get an error in HMS if you do this, but you might encounter some instability or some calculation errors. So just keep this in mind when you're setting your time step. And this can also be calibrated, right? This is just an initial estimate. And so depending on if you need more or less attenuation, to match your observed hydrograph, you can change the number of subreaches. And so in this example, number of subreaches 10 is more attenuation. If you have more subreaches, it's going to be less attenuation, so it's going to raise the peak higher. So calibration techniques, typically it's best to start with the rising limb, right? Match the timing first, and then match the attenuation or the peak second. And so we would start with matching this rising limb, and then we would adjust the attenuation parameters x and subreaches to better match this peak. So in this case, our peak is still a little bit too high, so I would probably adjust the parameters to get more attenuation. And as is the same for all the different methods in HMS, right, loss, transform, make sure to use these statistical metrics in addition to looking at the plots, because that just helps kind of objectively how well is the simulation, how well are your results. All right, advantages of this method. It's very mature. It's been used a lot. It's pretty old method that's pretty widely used, so it's very common. It's easy to set up and use, right? We just have the 3 parameters, and one of those is very physically based. So it's a very simple way to explain routing in the channel. The disadvantages is it might be too simple still, right? We're sort of representing translation and attenuation, but we're still simplifying those continuity and momentum equations. It's only appropriate for use in pretty steep streams, right? As we get flat, this method kind of falls apart. And the translation and attenuation is constant, right? So we can't change how much the attenuation is over the course of the simulation. You just have one K, X, and subreach parameter, and that applies for everything. So if your reach has variable attenuation, then this probably would not be a good method to use. And it also cannot simulate backwater effects. All right, the third method that we're going to talk about, and this is the last one we're going to go into detail on, is the Muskingum-Kunj method. And again, for the workshop, you're going to do each of these 3, the lag, Muskingum, and Muskingum-Kunj. Modified poles is another common one that we see used pretty often. So if you want to learn more about mod poles, you can read our documentation. But this method, Muskingum-Kunj, is essentially taking the Muskingum method and making some changes to it. And this was actually a really, really big deal. These were huge, massive improvements on the original Muskingum method. And it vastly improved it, and it made it a lot more physically based, right? So we're not using this like vague X parameter that doesn't have a lot of physical meaning, and we're replacing that with parameters that do have physical meaning. And so it ends up getting a lot of improvement in the results. So the numerical diffusion is equal to the physical diffusion. So this means the parameters can be more physically based rather than using this X parameter. So we have our continuity and we have our momentum equation. And so now for Muskingum-Kunj, we're going to make some simplifications. So this time we are keeping parts of the continuity equation. So we're looking at still kind of like the wedge prism storage. And then for the momentum equation, we're just keeping the first 2 terms, right? So as I mentioned, those terms over there, we're keeping the bottom slope and the pressure gradient, which are pretty good approximations if you remember from the beginning of the lecture, that guy that estimated like the magnitude of terms. The first 2 were the largest, especially in steep streams. So we're just cutting out these 2, which are the acceleration terms. And we're keeping the first 2 terms as our approximation. So in HMS, there's a lot more parameters. It looks a little scary, but these are actually pretty easy to find using GIS. It takes a little bit of time, but you will see vast improvements in the results over using some of the other methods, so don't be scared. Length and slope, we can get that directly from the parameter table in HMS. So if you have a georeferenced model and you have brought in terrain data, this length and slope we can get directly from those tables, no adjustments needed. Manning's N, right, this is based on the roughness in the channel. So there's a lot of tables out there that describe Manning's N for different types of like channel beds. So this is very well established. They use it a lot in hydraulics for RAS. We have this space, time, and index method, which I'll talk a little bit more about later. For the most part, you won't need to change those, but I'll describe what they mean. And then we essentially describe the cross-section of the channel. So there's a few different methods for that as well. But you can see over here, from the start of our channel, which is in blue, to the bottom of the reach, which is in the dashed black, the shape of the hydrograph has changed a lot, right? The last two methods, it kind of looked a little bit copied and pasted, maybe with a little bit of attenuation, but this time the shape of the hydrograph really changes, and that's because we're doing a better job of accounting for that storage continuity equation and the momentum equation. And so you'll see a lot more improvements in the hydrograph shape using this method. So we'll talk about the reach length and friction slope. As I mentioned, you can get that directly from HMS if you've brought terrain in. Oops. So that's these reach characteristics table, which we've shown before. This slope here is technically representative of the friction slope, but we approximate that using the slope of the bed of the channel. And so this is a stream profile, right? We can get the slope of the channel from that. We can also get that from within the characteristics in HMS. But the key thing here is that if you have changes in slope in the channel, it's best to split it up into different segments rather than just using one. So in this case, there's pretty variable slope, and you can kind of pick out the inflection points. And so I would do one channel from 5 to 4. I would do one from 4 to 2 and one from 2 to 1. So that just splits up so that you have more uniform slope in individual channel segments. If this slope was pretty similar across the whole thing, you could just use one segment for the whole thing. So just keep in mind, look at like that bed profile. In HMS, it's really easy to just adopt the values that it gives you without looking at what's happening within the channel. So if you have data for it, it's good to investigate that. Manning's roughness is very well studied, very well documented. You can typically find these values in a lot of tables. And so this is average for the whole reach, right? So even if there's a little bit of variation, the goal is to represent some average value of the roughness of the channel. You can use reference streams. So if you have streams that have been surveyed in the area and you kind of know what those channel characteristics are, you can use that. It can also be used as a calibration parameter. So the roughness will change the amount of attenuation that you get. This is just an example in Louisiana of like this type of ground surface had a Manning's N of 0.11. So it typically ranges from like 0.1 to 0.3. But yeah, it'll depend on the channel.
Question there.
Yeah.
So generally people just mention Manning coefficient roughness, but why you put there computed roughness? Why you use computed roughness?
So there were some studies go out and they actually do measurements essentially. So they use the Manning's equation to back calculate what the roughness coefficient is. Yeah, so that's this reference values. They've actually done calculations. Yeah, so it is fairly physically based, but there's a lot of tables. Alrighty. All right, so these two were the confusing, weird ones. Let me go back and, so that's this space-time method and index method. So these are essentially to help with computation stability. And so it's essential for accuracy and stability of the calculations. There's 3 space-time interval options. It's fine to just use auto. If there's a situation where you don't need to not use it, feel free to reach out to us for help, but auto is pretty much going to work for most cases. And then the index options are flow and celerity. Just use the celerity and use 5 feet per second. That has been shown to work very well for most applications. So for the most part, I would just leave it at these defaults. And then the cross-section. So this is going to be defining the cross-section of the channel. So there's 6 different shapes that you can use to define the channel shape. And this would be based on either terrain data or surveys done in the channel. The most common and probably the best one is the 8-point, which I'll describe. Circle, keep in mind that this is still supposed to represent open channel flow, right? So this isn't going to be like a pressurized culvert or anything like that. So just keep that in mind if you use circle. It's still open channel and not pressurized. This 8-point shape essentially it takes into account the overbank areas, so the floodplain areas, which is why it's a little bit of a better method rather than just the channel. And so we have, these are the 8 points along here, where 1, 2, and 3 represent the left overbank. We have 3, 4, 5, 6, which represent the channel. And then 6, 7, 8 represent the right overbank, right? So that's going to represent our floodplain area. So this is what it looks like when you put the 8-point channel in HMS. So there's a little cross-section that comes up. But if you can do more simplified, like if you know that you're not going to be modeling anything over the bank, you could use more simplified like the trapezoid or the triangle. All right, calibration techniques are going to be very similar to the other methods that we saw. So goal is to match first the rising limb or the timing of the hydrograph, and then after that match the peak discharge. And so for this method, you can see we're matching the shape of the hydrograph a lot better than the other ones. We're still a little bit overestimating the peak, and so we need more attenuation. For this method, since it's very physically based, a couple of things you can do is you can split the reach up into smaller reaches, right? So that might help account for this attenuation better. And then you can also use Manning's as a calibration coefficient. So for the most part, you're not going to be changing many of the other parameters like the cross-section or the slope or the length. Those are pretty much based on the GIS data, so those are not going to be calibrated. And as usual, make sure to use the statistical metrics to determine how well the calibration is performing. So advantages of this method is similar to Muskingum, but it has made a lot of improvements, and the parameters are more physically based, which make it easier to calibrate. It does have more parameters needed than some of the other simpler methods, but hopefully it's not too difficult to get that data, especially if you have any terrain or GIS data. It should be very easy to parameterize because it is measurable. And then the other benefit is that we can use overbank areas, right? So now we're not just restricted to the channel. If we go over the bank, we can model that a little bit better. And so this is particularly good for ungauged reaches. So if you don't have observed data, because this is so physically based, it's a lot easier to estimate the parameters without having to calibrate. So if you don't have observed data, this is probably the go-to method. The disadvantages, it also is limited to more steep streams. So if you have a flat area, we'll talk about which methods you can use. It also cannot simulate backwater effects, much like the other methods, and then it does require more parameters. All right, so with the reach routing methods, right, keep in mind that there are simplifications, and so we're making a lot of assumptions about the channel and about the equations that we're using. A method that's good captures the important parts of the system, right? Like You could use an 8-point cross-section on all your models, but if you don't need that level of information, then maybe a trapezoid or a triangle will be sufficient. So it's really a matter of what the conditions of the system and what kind of information you need in your results. And so keep that in mind. What are the study objectives? How detailed does it need to be? And how well do you need to represent like different aspects of the system? So just to rehash, when you're picking these methods, how well does it represent open channel flow processes, right? Because some of these are more simplified than others. Like the lag method does not include attenuation. So how important is attenuation in your particular reach that you're modeling? Keep in mind, we talked about some advantages and disadvantages. I have a table that we're going to look at the end. But like steep versus shallow slopes, backwater conditions, all of those. Not every method is going to be best suited for those different conditions. And what data do you need? What data do you have? So just continuing with that line of thought. What level of detail is needed? What kind of data do you have? And again, your familiarity, right? I think it's better to apply a more simple method very well if you're familiar with it than to use a method you're unfamiliar with and apply it incorrectly. And so if there's methods that you guys need help with, like if you're going to try to implement a new method for your study and you're not sure how to do it, feel free to reach out to us. We're always here to help. You're not going to be bothering us. So keep that in mind. Over here on the right, does anyone recognize that? Yeah. This is the Bay model. Has anyone been there? It's out in Marin. So Army Corps of Engineers had it's called the Bay model, and it's like a physical model of the entire San Francisco, San Joaquin Bay Area. It's massive. Like this is like hundreds of acres large building that contains this huge physical model. So this is what they did before we had computer models. And so they have all of these channels for the whole system. And something cool, can anyone guess what these like weird little metal spikes in the channel are? I heard sensors, I heard reference, not quite. Roughness. Yeah, who said that? Good job. Yeah, so the little random metal pieces were to represent like friction in roughness in the channels, and so they actually calibrated how many of those little spikes that they needed. So anyway, pretty cool. This is how we used to model channels, physically putting water through it. So it's nice we can do a lot better job with computers these days. Yeah.
Where did you say it's located at?
It's in Marin County, so it's just north of San Francisco. Yeah, just across the bridge.
Can you like visit it?
Yeah, so they have, you can go visit and like walk through yourself. They do tours. They still operate it a little bit. They're not really using it for data anymore. But it's cool because they literally like, if you go and visit, they have like a dam that they've built, and they'll just like lower it into the model so they can simulate, what if we built a dam here, what would happen? Yeah, and it counts for like tidal, like moon phases. Yeah, pretty cool. I highly recommend if you're like, have extra time on your hands before you fly out, you could try to make it down there. It's hard to get to without a car, but all right. All right, so there were a couple of like special conditions that we mentioned that most of these methods are not good for. So we're going to talk about which those are. So the first is backwater effects. So if you have like hydraulic structures, tides, culverts, any obstruction in the river, you're going to get some like backwater effects, right? So this is kind of like a piling up of water, and that changes our storage in the channel. So that's why a lot of these methods that use like simplifications of the continuity equation, right? That's our conservation of mass, that's our storage one. Those assumptions kind of fall apart when we have these backwater effects. So that's why a lot of these methods don't work. So for the most part, hydrologic methods cannot simulate, except mod poles. That's one that can simulate backwater effects. So if you know that that's a big aspect of your channel, like there's a lot of hydraulic structures, this might be the method to use. Again, feel free to mix and match. If you have one reach that has backwater and one that doesn't, you can use different methods on those. Hydraulic routing typically does. And so if you have, like if this is a really big impact on your system, like it is for the Sacramento River, you might want to just use RAS, right? HMS can only do so much. We make a lot of simplifications. Floodplains is also one that only a few of the methods can simulate. So these have a very big impact on the hydrograph, especially if it's common for the flow to go over the banks. And if it's really, really wide, that's a huge amount of storage that's being accounted for in this overbank areas. And especially roughness. Roughness tends to change a lot once you get into the floodplain area, and it really, really slows down the hydrograph compared to when it's in the channel. So the best way to model this is to separately model the channel and the overbank areas. So Muskingum Kunj we mentioned with the 8-point channel. It does have a separate Manning's N for the overbank and for the channel. So that's one way to represent it. So as I mentioned, Muskingum Kunj, modified poles is another one that can model floodplain areas. And as I said, you can have a separate Manning's N for the overbank versus the channel, which is important for modeling those separately because again, they change the flow, they change the hydrograph in very different ways. If you have very wide and flat floodplains, if you are using HMS, the 2D diffusion wave, which Greg talked about yesterday as part of the transform lecture, that can handle floodplains a little better. If it's especially flat or especially a lot of hydraulic structures, again, you'll probably need to just go straight to RAS for that. Confluences and flow splits, right? So this is where we have two rivers coming together. A lot of times that can cause backwater effects in itself. And so these are the two methods that are appropriate if you have really big confluences that cause backwater. So that'd be 2D diffusion wave and modified poles. But again, if it has a network with a lot of flow splits or even flow reversals, right? Sometimes backwater causes flow to go upstream. Then you should be using full dynamic wave, which is going to be RAS. So we can't do that in HMS. Supercritical flow. Does everyone remember this from fluid mechanics a little bit? Draw some pictures. So if we have a channel, let's say it starts out pretty steep and then it changes to flat. Supercritical flow, there's a couple of ways that we calculate it in fluid mechanics. But essentially, if we have our, let's see. If we have our flow in the channel, and let's say it's supercritical at this point, and so it's uniform, and then we get to this change in slope, that can cause what's called a hydraulic jump. So that's a sudden change in the flow characteristics. So we go from supercritical to subcritical. And when you go from supercritical to subcritical, it's always a sudden change. It's never gradual. You're going to see a very distinct change. So if we were to go here, there would be that kind of jump. Has anyone seen that before? Remember that a little bit? Bringing back some memories. Does anyone here raft? River rafting? A couple? Okay, I see a couple people. Have you ever dumped from a hole? I don't know. Okay, so a hole in rafting is it's essentially a hydraulic jump, right? So there's a sudden change in slope or a lot of rocks, and it creates this hole behind the rapid. And so when you're rafting down and you get into that hole, it essentially flips you over because of this sudden hydraulic jump. So that's called a dump truck. All right, anyway, supercritical flow, hydrologic methods cannot simulate that. Essentially, Don't use HMS if you have supercritical flow. If you have these hydraulic jumps happening, you'd have to go to RAS for that. If there's small intermittent sections that have supercritical flow, that can be ignored. So just be aware of how important is that in the reach. Maybe you start using a certain method or start using HMS, and you realize that you're just not able to calibrate very well. It could be one of the reasons. So keep that in mind. All right, so observed data, right? That's the best way to calibrate. If you have it, if you don't have it, then it's better to use those physically based methods, so like Muskingum-Kunj, which are very physically based. If you don't have observed data, that usually gives a pretty good estimate just using those, GIS terrain data. So that's going to be easier to estimate, and it's going to be more reliable than using a method like lag that's not very physically based. If you do have observed data, which ideally you do, please always calibrate, even if you use one of these methods. Right? We want to make our models as useful as we can. Like I said, all models are bad, but some models are useful. So the goal is to make ours as useful as we can. So again, these statistics are down here in your output, so you can measure the quality of the results. So with channel slope, I mentioned that the steeper channels perform better with the hydrologic routing methods. And so especially like in this area, so this is a kind of plot of the profile of the channel bed. And in these steep areas, it's going to perform a lot better than some of these flatter areas. And so if I were to run this in HMS, I would consider splitting the reach here and using a different method for this part than I use for this part. So just keep that in mind. It's really helpful to have stream profiles, especially on like the larger channels that you're modeling. So as I mentioned, like when it becomes flat, those three terms on the end, the pressure gradient and the two acceleration terms become a lot more important, right? So that's where our simplifications start to fall apart. All right, a couple of rules of thumb for slope. When the bed slope is very steep, that's good. Most methods will work. That's kind of how they were developed, and our assumptions are going to be more correct. When we have a very low slope, most of the methods are going to produce erroneous results. So at that point, you would probably consider using RAS, depending on your study needs. In between those, between 2 and 10 feet per mile, that's kind of the gray zone where sometimes they'll perform well and sometimes they won't. And there's a couple of metrics we can use to determine whether our method is going to be appropriate. So we're going to talk about that. So these Ponce criterion, I know you thought you were done with equations for today, but we're not. So Ponce in 1978 came up with these criterion to essentially say how well are these approximations, and that tells us how well our methods might apply. So if you're in that gray zone of 2 to 10 feet per mile, if you're feeling very eager, you can calculate this criteria, and it will tell you whether or not a certain method is appropriate, right? So that says, can I use Muskingum for this reach? That's 5 feet per mile. And so these equations are based on essentially the velocity, bed slope, and flow depth. This is information you can get or derive. And so if you were to calculate this criterion and it's greater or equal to 171, and then we say that the kinematic wave approximation, which is just the first two terms, or the first term, right? So friction slope equals bottom slope. That's the kinematic wave approximation. So if we meet this criterion, then we say that that approximation is good, is okay, which tells us that we can use those methods in HMS. There's a second criterion, which is for the diffusion wave approximation. So that's the first two terms, which is bottom slope and pressure gradient. And so if we calculate this criterion and it's greater than or equal to 30, then yes, our approximation is okay. We can use those methods in HMS. So I'll show a couple of tables that kind of summarize that, because I know that's a lot to remember. So There's those tables. If you have no observed data, then you're going to be using a more physically based method, which are these listed here. And we have a little asterisk on modified poles. It's only appropriate if you use storage discharge curves that have been developed by hydraulic model, right? So if you don't have observed data, that's how you would get those curves. If you don't have observed data, you should not be using these two methods because they're not very physically based. You really need observed data to calibrate to. And keep in mind, these aren't like hard and fast rules. If you want to come argue with us that, hey, I want to use this method for this condition and you can defend why, like that's okay, but this is a good rule of thumb. If you have significant backwater effects, you're pretty much limited to diffusion wave or modified poles. Most of the other methods cannot simulate backwater effects very well. And if you have floodplain areas, these are the three methods that we can use. And then Muskingum-Kunj, that's only if you use that 8-point cross-section, right, that has the floodplain area. These other methods cannot be used. All right, more tables. So this is the Ponce criterion, just to re-summarize. So if you have a high slope over 10 feet per mile, pretty much all methods are going to be applicable, right? All of our assumptions are going to stand up. If we have this like intermediate slope between 2 and 10 feet per mile, and our Ponce criterion, right? So this is our kinematic wave approximation. If that fails, then these are the methods we have to use, right? So kinematic wave approximation failed, so we cannot use it based on this criterion. If you have a low slope, depending on the Ponce criterion, if our diffusion wave approximation, right, so that's the first two terms, if we use the Ponce criterion and say that approximation is okay, then these are the three methods that we could use for lower sloped areas. If we have really low slope and we don't meet our Ponce criterion, then we just have to go full dynamic wave, which is RAS land. So we're not able to simulate that in HMS. So that's kind of how those Ponce criterion come into play. Hopefully your slopes are high, so you don't even have to worry about it. But I know there's a lot of areas where there's pretty low slopes. All right, made it through. So just to summarize, we have a bunch of different methods in HMS. They make different levels of approximations. So some do a better job of representing attenuation. Some don't represent attenuation at all. All of them represent translation to some effect. So we talked about lag, Muskingum, and Muskingum-Kunj. So those are the three that we're going to do in the workshop right after this. But the most appropriate method just depends on the conditions of the channel, the slope, just keeping in mind those approximations.